then I'm going to present. Okay. So while I'm presenting, I'm unable to see the chat window. So please interrupt me verbally. Okay. So that I can know that somebody has a question. All right. All right. So I'm eagerly waiting for the first question. Okay. So the challenge for you is to ask a question in the very first slide. All right. So my name is Ashutosh Mahajan. I am at IEOR, which is Industrial Engineering at IIT Bombay. I don't have any affiliation to aerospace engineering, much like some of the other coordinators of this workshop. And I don't do a lot of multidisciplinary design optimization. I work a lot in optimization applied in operations research, in which you have to take decisions to make the operations of industry and service systems efficient in order to save costs, give better service, and so on and so forth. So you can think of Indian Railways, for example, and they have design and engineering divisions, but their main operations are running trains, and we would all like trains to run on time and in the best possible manner, and that is an operational problem, and how do you manage those things, and how do you optimally run that system. So those kinds of problems are popular in IEOR, and they are very different from design problems. But the underlying theory of optimization and how it is used is pretty much the same, and hopefully you will get a flavor of this today. Okay, so agenda is to understand and get an overview of nonlinear optimization. In many universities, nonlinear optimization is taught as a course in postgraduate programs, and it's a semester-long course with 40 hours or so. We only have 90 minutes to just get a glimpse of it. So I'll try to give you the basic ideas. Okay, and after 1.5 hours, we will switch to doing things hands-on. We will run things in Scilab. I hope all of you have installed Scilab, and the FOSSEE optimization toolkit instructions were probably shared with you earlier a few days back. And I have already posted the link of all material. Hopefully you are able to see it. So can anybody quickly say that they are able to see this material online? I'm not on chat, so you will have to verbally say it.
Yes, sir, it is showing in the drive.
Fantastic, fantastic. All right, thank you, thank you. All right, so this was a question that I asked, and it was a very simple question. So similarly, next slide onwards, it is your duty to ask questions. Okay. All right. So so let's start. Okay. On the screen, you will see a blurry image of some mathematical equation, 0.05 x to the power 4 plus x minus 6 whole square. So this is a function which is given to us, and it has only one variable x. Okay, and like all courses that we teach, one has to find x. Okay, and we want to find an x where this function will take the minimum value. Okay, so in this session we are going to be pessimistic, and we will always try to minimize. Okay, we would like to minimize cost, or minimize some distance, or minimize some time, or whatever, right? It doesn't matter what the modeling application is. We will focus only on the nonlinear optimization part. Okay, so suppose somebody gave you this function and said, can we find the minimum value of this function? And since all of you are doing this MDO for a few days now you know what are the possible approaches, right? So one is you can do some hit and trial type of methods. You can sample x, you can pick some random values of x, get the values. Based on the values you got, you can try more values of x, and you could derive some heuristic methods based on that, right? So you can do a lot of smart things just by finding values of x at many different points, and that is probably covered under the topic of heuristics. Okay, so either evolutionary algorithms or hit and trial type of methods or randomized algorithms, like simulated annealing or genetic algorithms or such. So you can try many different x and then combine those values in certain interesting ways and try to reach the minimum value. Okay, or if it's a one-dimensional function, what you can do is just simply make a plot and then see the shape of the function and find the minimum value, right? And that's what many people might actually do. Today we will talk about how to mathematically go about doing it in a systematic way, in an algorithmic way, and so that we have some guarantees that we will reach the optimal point. Okay, and from basic courses in high school or even college, many of us will know that given a smooth continuous function, the point where it will take a minimum value, the derivative actually becomes zero. Okay, so mathematically we can set the derivative to zero and then say that at what points that derivative is zero, and that might give us a point of minimum value. Okay, so that is very straightforward and simple. Okay, but things become complicated very fast. Okay, uh, and for example, this plotting works for maybe one variable, or if you have two variables in your function, then you can do some plots. Beyond that is just too difficult. Okay, uh, and heuristics also have a great place in optimization. But sometimes you are interested in some proofs and saying formally, can there be some guarantee that there is no better solution? And for certain types of problems which are well behaved and have nice derivatives, you can actually devise methods where you can give a guarantee that there are no better solutions. Okay, rather than just running some heuristics for a long period of time, you can actually say that for this problem, there is a guarantee that there cannot be a better solution, no matter where you search. Okay, so there is some advantage of doing things mathematically and rigorously and systematically. All right. Okay, so in today's class we will focus only on derivative based methods. So that means all the functions that are given to us, they have derivatives. Okay, so remember that not all functions have well defined derivatives. And many functions cannot be evaluated also at some points. Okay, so for example, look at the function 1 upon x, right? Its behavior is strange at x equal to 0, right? And you would not like to minimize or maximize over this function near 0, because there the behavior is very tricky. Okay. Similarly, if you look at the function square root of x, okay, so square root of x is a nice function, and at least when x is positive, then it is well defined. Okay, and it is well defined at x equal to 0 also, but its derivative is not really well defined at x equal to 0. So derivative of 1 upon derivative of square root of x is 1 upon 2 square root of x. So the square root of x comes to the denominator when you look at the first derivative, and that creates problems when x is close to 0. Okay, so we will assume that for now at least, that whatever functions will be given to us, we will not have these problems. So derivatives will exist, and they will be nice and smooth and continuous. Okay, and we will see later through some examples that when you are in the nonlinear world, then you might be at a point which is locally minimum. So that means if you look around that point, you will not find better solutions. But if you go far away, then there is a chance that you might find a better solution. Okay, so imagine standing on a hill, and then if you just look around yourself, then everything is going downhill. and that means you are at the highest point. But if you go far away, you might find a taller hill, and you might want to climb it. Okay, so that is a example of a locally maximum point. Okay, so similarly, you can think of locally minimum points, and what the algorithms that we studied today, they will try to reach to local minimum points, locally minimum points, right? The finding globally minimum is somewhat more rigorous and difficult, and we will leave it for some other session. Okay, not today. Okay, and also these methods that we will talk about, they will be iterative methods. So there will not be a closed form solution saying that you apply this formula and you will get the optimal point. Rather, these methods will be numerical methods in the sense that you would have an algorithm which says step 1 do this, step 2 do this, step 3 do this, and then go back to step 1 again, repeat step 2, step 3, step 1, step 2, again and again and again until you find a point where you can stop. Okay, and the methods that we will talk about are well established and well known, and today there are software available which can rather quickly find solutions to these problems with up to 1 million variables and such. Okay. And of course, sometimes there are constraints also. So you may say that x cannot take these values, or x should satisfy some other relationships. So those are called constraints, and we will look at those as well in today's class. All right. Any questions so far? Nobody? Nobody. Oh,
No, sir.
thank you. Okay, so we will look at two classes of problems. One are called unconstrained optimization problems. That means you only have objective function and that's it, right? Just like the example I showed you right back, you want to minimize a certain function, that's it. And there are no restrictions on what x can take, right? So those are called unconstrained optimization problems. That means problems without any constraints. And there are a lot of methods available for these types of problems. Some of them are listed here. Quasi-Newton methods are pretty good. Conjugate gradients, trust region methods, they are all quite nice. There is a lot of interest, not only from design applications, but also from machine learning and data analytics side of things. And those people recently have started using a lot of these methods. So there's a lot of interest, and there are a lot of new developments in these methods, especially for very, very large scale problems. Okay. Constraint optimization problems, these are problems that have additional constraints. So you don't just say minimize f, you just say minimize f subject to some other conditions. And there, the applications are mostly from design and industrial operations. And there are, again, there are many methods available. Two broad classes of methods, practical methods, are these active set methods, which include sequential quadratic programming and sequential linear programming. As the name suggests, you solve a series of quadratic problems or linear problems and try to reach the optimal point. And these are called active set methods because they try to guess which constraints will be active at the optimal point, and then they try to search in those regions. Okay. On the other hand, interior point methods are those which move from the interior of the feasible region, and we will see some pictures to understand this part. Okay. And they move iteratively to a better and better point and converge to the optimal. Okay. They are also called barrier methods. We will see why later. Okay. So these are some very, very broad classes of methods to solve problems. Okay. These are some references, some nice books. My favorite is the top one, Practical Methods of Optimization by Roger Fletcher. Roger Fletcher was one of the leading figures in nonlinear optimization, and he passed away about 2-3 years back. But his book has been seminal and useful for all types of applications and all types of people who would like to use optimization. The book is a bit dense and condensed, but the other second book by Nosedal and Wright, it's a largish book and somewhat more expensive, uh, but it is far more detailed and goes slowly through all ideas, and is more suitable for teaching in class. So practical methods, or the first reference and the third reference, they are easily available in India, and not too expensive. Okay, the others may be somewhat expensive. This last book that I have mentioned, Boyd and Vandenberg, this is, I think, freely available, but this is limited to convex optimization, where all functions have are convex. So we will look at convexity also later on uh, in today's lecture. All right. So as I said, a general nonlinear optimization problem is one where you have a given function f of x, and this f of x is called the objective function, and we would like to minimize f, but at the same time satisfy some constraints. Okay, and when there are no constraints, we call it unconstrained optimization, and when there are constraints, we say constraint optimization. When your constraints are all linear functions, then we know a lot more about those problems, because linear functions are easy to analyze and they have some very nice properties. So you can develop some very fast algorithms, uh, which may not be useful for general nonlinear problems, but they are definitely fast and useful for problems which have linear constraints. Okay, so a lot of algorithms are devoted to the case where constraints are linear, and in many cases, in many models and applications that you see in engineering and business, in fact, many constraints tend to be linear, because a lot of modeling uh, gives rise to linear relationships. Okay, so in practice, many constraints are actually linear. Okay, and there might be few or zero or small number of nonlinear constraints in some PhD type problems, and in some design of some very complicated systems, you might actually have many nonlinear constraints as well. Okay, so it's not that you never have nonlinear constraints. Sometimes you have just too many nonlinear constraints as well. Okay, so you have different algorithms depending on what type of constraints and objective function you have, right? So if all constraints are linear, or they are just bounds on x, then you use somewhat more sophisticated and easier looking algorithms. On the other hand, if constraints are nonlinear, then you use a different type of methods. Okay, so it's not that these 5 methods are the only methods. Okay, so depending on your problem and what you want to solve, your algorithms will differ. Okay, and it's a very active area of work. People develop new and new algorithms every year, and we gain a lot of understanding in terms of properties of these problems and analysis of these problems, and how to make methods faster and more reliable and robust. Okay. So algorithms are typically iterative, like I said, and the general scheme is this: you visit one point, check whether we can stop there, and then you move on to a better point. And this is mostly true for all optimization algorithms. Okay, where you try one point, then try to improve upon that point somehow. Okay, either by looking at certain directions, or fitting some smaller optimization model to it, or by looking at past data, or some other property of the problem. Okay, but mostly all optimization problems are this scheme: you visit a point, check if we can stop. If you don't want to stop, then try to find a better point, and keep repeating. Okay, two things that help us a lot in in these algorithms and especially these nonlinear optimization problems are these ideas of derivatives and neighborhoods. Okay, and that is what we are going to see in a little bit. Okay, so what is a neighborhood? So suppose you are at a point, let's say x equal to 0. What will be your neighborhood? Your neighborhood will be the points which are around you, right? So you can draw an interval or a ball around yourself, and whatever points fall in that ball, they are called your neighborhood. If that ball is bigger in size, you say it's a large neighborhood. If it's a very small sized ball, then you say it's a small neighborhood. Okay. But if you know, so suppose I am at x equal to 0 and I know the function value at current point is say 10. Okay, then I know that around x equal to 0, the function value will be near about 10. Okay, it will change in some way. Okay, definitely. But it can't go too far away. Okay, unless the problem is very poorly behaved. Okay, so if there are numerical difficulties in the function, then it may jump around wildly. But for most smooth functions, okay, the function value is not going to change too much in the neighborhood. Okay, and that helps us developing some rigorous mathematical ways of analyzing things. Okay, and the most important tool, it turns out, is the Taylor series. Okay, the Taylor series is so important in engineering. Every college, every university teaches this in the first year, and this is by far the most important tool in nonlinear optimization as well. Okay, so we will look closely at this as well. Okay, so that is the end of my slides, and now I'm going to switch to writing mode. Okay, so that I can explain some maths, draw some pictures, and so on and so forth, which are just too difficult with slides. Okay, so if you have any questions until now, please feel free to ask.
No, sir.
Okay, all right. So let me see if I can make this go away. All right. So hopefully you are able to see a black screen and things that I scribble on it. Okay. If you are not able to see it, let me know. Okay. So we will start with a very simple problem and see what kind of approaches we can use to solve it. Okay. So let's take a very simple example whose solution most of you would know. Okay, so let me write a problem. Let's say minimize x1 square minus 2x1, okay, plus 7. Okay, and I'm minimizing over x1. All right, is everybody able to see the scribbling that I'm doing?
No, sir.
Please share the screen, sir.
Oh, yeah, just hold on then. All right, is something visible now?
Yes, sir, visible.
Okay, so I have written a very simple optimization problem. So who can tell me whether it's constrained or unconstrained? This is unconstrained, okay, because there are no constraints. Okay, if I add some constraints, suppose I say subject to, let us say x1 less than equal to 10 and greater than equal to 5. Okay, so then I have added a constraint. I'm saying that x1 is constrained to be between 5 and 10. So then it becomes a constraint problem. Okay, so that we will look at later. Let's just look at this simple case of one single very simple optimization problem, and the way you solve it is very simple, right? In your high school, you know that you just take the derivatives. Okay, so let's say this function is f. So I'm just going to evaluate partial derivatives with respect to x1 is what? Is it 2x1 minus 2. Okay, so I know that x1 equal to 1, okay, is a stationary point. Okay, and what does a stationary point mean? Stationary point means that the derivative is 0. Okay, when we are talking about derivatives in higher dimensions, so when we have say 5 variables or 10 variables or such, then we don't use the term derivative, we use the term gradient. Okay, so this is something we will use again and again in today's class. So we say that the point where gradient becomes 0 is called a stationary point. Okay, and one can see the plot of this function. So my horizontal axis is the x-axis, the vertical is the function value. Okay, and if I plot it, then it will be some parabola type of a function which goes down and up. Okay, and by looking at the plot, you can find out what is this optimal point. Okay, and it turns out in this case it is x star is 1. Okay, so and even if there is a function which has a different shape, so for example a shape which looks like this yellow curve, then even the maximum point of the highest point or the maximum point, that also has derivative 0. So that again we know that when you look at the second order information, then if it's a positive, then we know that it's a minimum point, and if the second order derivative is negative, that means we are at a maximum. Okay, so so that much we know. Okay, but now let's go to somewhat of a complicated function. Okay, so suppose I say let's try to say minimize x1 square plus 7 upon x1 square plus 5 plus cos of x1 plus let's say log of 1 plus x square. Okay, so again it's a problem in only one variable. Okay, and there are no constraints, but now it is somewhat complicated. Okay, using your high school understanding of functions and such, you can plot it, but still it's not going to be easy to plot. Okay, so this is not easy to plot. And the function may actually go up and down, who knows. I just cooked up this function right now, so I don't even know the shape, right? So the function plot may look like something going up and then down and something in between. Okay, but it is nice and smooth because all these functions are nice and smooth. Okay, so my function plot might look like this. Okay, so what I can say is that if I look at these yellow points, Okay, I will call them local minimum. Okay, because I don't know the behavior of the function as I go far away. Okay, it's a complicated function, and maybe if I plot it towards the left, okay, then the function may actually come down by a lot, and it might have a even better solution than these local minimum that I have drawn. Okay, so for example, it might just go down very fast later on. Okay, so global minimum maybe somewhere else. Okay, so is this clear that if a function is wavy and going up and down, then it might have points which are locally minimum, and that means they are minimum within some neighborhood. Okay, so if I take a yellow point and draw a circle around it, then within this circle at least this point is the minimum. Okay, or if I'm at the graph, okay, I look at the interval around x star equal to 1 and look at this shaded region, and within this shaded region this is probably the best value. Okay, it turns out that for this simple function x square minus 2x1 plus 7, this is also the global minimum. Okay, so this is local as well as global. Okay, but in more complicated functions, this local minimum may not be global. Okay, the global may be somewhere else. Okay, or who knows where it might be. Okay, because the function is varying up and down quite a lot, so it's a bit difficult to see where it might hit the global optimality. Okay, so in this class we will not try to find a global solution. Okay, we will try to find a local solution, and in many applications that is good enough. Okay, that is better than not optimizing at all. Okay, and also if you have a fast algorithm for local optimization, then you can randomize it slightly, and then it might find many local optima, and then you can pick the best out of those. Okay, in the hope to get closer to the global solution. Okay, so one difficulty with the setting derivatives to 0 and finding the roots is that the function itself might be quite complicated, and if I try to find the derivative of this function, so what is df by dx1? Okay, I doubt anybody of us will know it just orally doing it. You will have to take pen and paper, write things down, and then set it to 0, right? So some complicated nonlinear function will come here, and if I set it to 0, it's not very clear how do you find that x where this function will become 0. Okay, so you will have to use some numerical method like Newton-Raphson or secant based or something to find the zeros of the derivative. Okay, so it's not going to be easy even for one-dimensional function. Okay, typical functions are multidimensional. Okay, so that means you don't have just one variable, you might have multiple variables. So for example here, okay, let's say this minimize over x1 and x2. Okay,
Sir, I am unable to see your screen.
Sir, your screen is not visible, sir.
just hold on. Just hold on. Let me share again. No, so I don't know why it keeps unsharing the screen again and again. Okay, is it visible now?
Yes, sir.
Yes, sir.
Oh,
Yes, sir.
Okay, so now for our next example, let us look at a function which has two variables. Okay, not just one variable. Let's have two variables. Let's say 4x1 square plus x2 square. Okay, that's it. Okay, so this is a very simple function. It is a sum of squares. So we know what is the solution. Who can tell me what is the optimal solution to this? It's a very simple thing. At which point will this function take a minimum? 4x1 square plus x2 square. Very quickly. It's the simplest point you can think of. 0, 0. All right, because at all other points the function will be positive. Okay. All right. But how do you plot it? You know, it's not even clear that how do you plot it on a piece of paper, right? So if you are already familiar with it, you can do contour plots. Okay, so many of you might have seen them. So contour plots plot. So no longer you have function value plotted in the graph. Rather, your horizontal axis is x1 now, vertical is x2, and instead of plotting f, you plot the points that have the same function value. Okay, so you draw level sets of the function value, and in this case it might look like some ovals. Okay, so this curve that I have drawn is 4x1 square plus x2 square equal to 1 maybe. Okay, and then as I increase this 1 to higher numbers, it will give me bigger and bigger ovals. All right, so this last one might be 4x1 square plus x2 square equal to, let's say, 20. So, right. So you can do these contour plots with some effort, but it will take some more time and effort, right? And by looking at these contour plots, you can see which direction the function is increasing or decreasing. Okay, and if you have a nice program that gives you contour plots, you can even spot the optimal points. Okay, but now suppose you have even more variables, and let's say there is a third variable. Okay, plus let's say x3 square minus 2x2 x3. Okay, so now there are three variables. Now you can't even do contour plots. Okay, so this geometric interpretation is good for understanding how algorithm works, but they don't help you in solving practical problems. Okay, after a certain while. Okay, so two difficulties we have seen. One is that in higher dimensions there is very little geometry that we can imagine. And also even in low dimensions, if the functions are complicated, then it's not that straightforward to compute where the optimal value is. Okay, so for example, if you have these log functions, exponential functions, trigonometric functions, and so on. Okay, so that is why we need these numerical methods. Okay, which don't rely on plotting, and they don't rely on just setting derivative to 0 and then trying to compute at which points that derivative is going to be 0. Okay, so here is a numerical method. Okay, so these are step-by-step methods. For example, so let me tell you, give one template for a numerical method is you pick a starting point. So you pick any point from where you want to start. Okay, and it doesn't matter what you pick as your starting point for now. Okay, let's call this x with a superscript 0. Okay, so remember that subscripts. Okay, so when I say x1, x subscript 1 and x subscript 2, those are the variables. And if I say that x superscript 0 or something, that means it's a vector. Okay, so it has two components in this problem. For example, it might be x01, x02, x0n. Okay, if there are say 5 variables, then this will be a vector of size 5. Okay. So this is your starting point that you will pick. Okay. Then you compute a direction. Okay, so find a direction in which you would like to move. Okay, so let's call this direction dk. Okay, so intermediate step I will set k equal to 0. So this is my iteration count. Okay, so how many steps will I need to solve this optimization problem? That is not known beforehand. Only after you solve, you would know how many steps it took. Okay, so you set k equal to 0 and then find a suitable direction in which to move. How do you find that direction? We will see later. Okay, so let's say you call this direction dk, because this direction will keep changing in every step. Okay, so again this is a vector. Okay, same size as the number of variables. Okay, and then you move to a then you decide how much to move. And then you move that much. And then what do you do? Okay, then you check whether gradient is 0. So what is the symbol for gradient? Gradient is this thing called nabla, which is an inverted triangle, and check whether gradient of f is 0 or not. Okay, and if it is not 0, then you go back. Okay, so then you increment k equal to k plus 1, and go to step number 3. Okay, and you go back and again find a new direction in which to move. Find dk, decide how much you want to move. Let's call this alpha k, and move that much. Okay, so we will say that xk plus 1, my new point, is same as my old point plus the step length times the direction. Okay, is this clear? So let me tell you geometrically. Okay, so geometrically what I will do is, again, suppose I have two variables, x1 and x2. So I'm in a space of these two variables. So let's say any point. Let's say I'm at 1, 1. Okay, and I'm at this point. I will find the function value at that point. So I will say, what is my function value at 1, 1? Okay, then I will say, let me pick a direction to move in. And how many directions are there in which I can move? Who can tell me? From 1, 1. Suppose I want to move to a different point. How many directions would there be? Who can tell me?
Kindly repeat, sir, your question.
So my question is, currently I am at point 1, 1, and I want to move to some other point. Okay, to move to a different point, I need to move along some direction. Okay, either I can go up or towards the right or towards the northwest side or northeast side. So in how many directions can I move? Possibly.
Finite, sir.
Infinitely many. Very good. Okay, so so either I can go up or slightly up and towards the left, right? So there are potentially many directions in which I can move. So out of these directions I need to pick one. Okay, so I will pick one direction somehow, and I will call this dk. Okay, and once I have selected a direction, okay, then suppose I choose this blue direction to move. Okay, let's say I want to move in this blue direction. Somehow somebody came and told me that if you move in this blue direction, you will reach paradise. Okay, so then you start moving in this blue direction. So the next question is, how far is paradise? You know, how far do you need to go? Okay, so that is called the step length. Okay, so once you fix the direction, so this dk is called your direction, and this alpha k is called your step length. Any questions?
No, sir.
Okay, so these, you know,
No, sir.
this broad scheme of things gives rise to many algorithms. Okay, so let's try to understand just one algorithm out of all these. Okay, which we will call steepest descent. Okay, so the steepest descent algorithm. Okay, so again I will write the steps of the algorithm, and it goes as follows. Step 1 is select a starting point. Okay, if you don't know how to select a starting point, you can use origin 0 0. Okay, safest bet. Okay, let's call this x naught. Okay, I will set my counter to 0. Okay, this is my iteration count, tells me how many iterations I needed to run my algorithm, and then I will go into a loop. Okay, while not converged. Okay, so keep doing some steps until I converge. Okay, and what are those steps? Okay, so step number 4, okay, is um, set dk to be the minus of gradient of f of xk. Okay, so that means I'm choosing a direction. So this is my direction step. Okay, so I evaluate the gradient of f, and the gradient of f is a vector. So we will do an example and see. Okay, and I choose the negative of the gradient. Okay, so and I will explain to you why we choose the negative of the gradient. Okay, so number 5 is do a line search along dk to find step length, and this I will say alpha k. Okay, next step is update. So that means I actually move to the new point. So xk plus 1, the new point is the old point plus step length times the direction. Okay, and then I set k equal to k plus 1, and that's the end of the while loop. Okay, so I keep doing this again and again. Okay, so it's easy to see that it is following the scheme of the algorithm that I mentioned earlier, right? You find a direction, decide how much to move, and then move. Okay, so there are 3-4 questions to ask. One is, how do you select a starting point? That is not that critical. Okay, you can choose origin or any other your favorite point, 42,42 or whatever, right? So the questions are these. Okay, how do you check convergence? How to check convergence? Okay, that's number one. Number two question is, how do you do this line search? Okay. And then maybe some small questions about why we have chosen gradient, minus gradient as decay and others. Okay, but as far as implementing this algorithm is, we need these two things, and usually the convergence check is just the norm of the gradient. Okay, so we say that there are various ways of checking convergence. One is you can say that did the function change a lot from the previous step. If the function value is not changing much, in every step, then you basically stop. Okay, or you check the gradient of the function, and if it is 0, that means the derivative is 0, and that means we are likely to be at an optimal point. So then also you can stop. Okay, so one convergence criterion is this, that you check the norm of the gradient of f of x at k, and if this is clearly 0, then you stop. Okay, otherwise you do one more iteration. Okay, and then the question is, how do you do this line search? So line search is another algorithm. So this is an algorithm within an algorithm, and we will not go into too many details of how you do this line search. But basically, you sample some points on this line, and based on the function values at that point, and sometimes the derivatives at that point, you choose newer points, and there is a guarantee that that line will give you a point if you do that. Okay, so so we will not do line search. If you are interested, you can email me later. I can point you to some resources which explain line search in detail. Okay, so we will not today. Okay, so we will not do line search today. Okay, otherwise we will not be able to do anything else. Okay, but there is a way to search along a line in higher dimensions by sampling some points and finding some good intervals in which we are guaranteed to have a good point, and then trying to find that good point. Okay.
Excuse me, sir. Sir, somebody is asking why the gradient is negative.
Why did we take a negative of the gradient? Okay, so that is something I wanted to discuss, and also explain this idea of the derivatives. Okay, and neighborhoods. Okay, so let's start with a very simple one-dimensional example. Okay, no, not even two-dimensional, just one and basically the original function. Okay, so original function was x1 square minus 2x1 plus 7. Okay, so let's take this x1 square minus 2x1 plus 7. Okay, and let me pick any arbitrary starting point. Okay, let's pick 0 0. Let's say my starting point is 0 0. Okay, what is my gradient? Okay, so what is my gradient of f? Actually, this is just a one-dimensional problem, so I don't even need a vector. So let me just write it in a vector form anyway, right? So it is a vector of 0, right? So so what is the gradient of f? Okay, it is 2x1 minus 2. Okay, that's it, and it has only one component. There are no multiple components. Okay, and if I evaluate it at 0, so what will I get? At the point 0, its value would be minus 2. Okay, so we know that when gradient is 0, it tells us that we are at a locally minimum or locally maximum point. But if gradient is so for example, it says it is minus 2, then what do we mean by that? Okay, so geometrically what it means is that so I am at x equal to 0, so that means I am at this blue dot. Okay, so this minus 2 is telling me the slope. Okay, so the slope is this way. Okay, if I draw a tangent at this point to the curve f, then this slope is -2. All right, and what does this -2 mean? Okay, so what this slope generally means is that if I move from x naught to x naught plus epsilon, okay, so suppose I move slightly towards the right, okay, what, how will my function change? Okay, so again look at this curve. Okay, what is this line telling me? Okay, this line is telling me that as I move towards the right, the function value is going down. Okay, that's the meaning of -2. It says that if I go from x naught to x naught plus epsilon, my function value at x naught was what is the function value at 0 0? It is 7, right? If I evaluate the function at 0, this is 7, right? So if I move slightly towards the right, okay, what would be the function value? It would be 7. Who can tell me? Who can tell me the answer? Right? Approximately, if I move slightly towards the right, okay, it will be 7, but slightly different from 7. So who can give me a better estimate than 7? Anybody? 6.9. So that means it is going down. But suppose I take a epsilon, small epsilon, and I don't tell you what is that small epsilon. But roughly speaking, by looking at this gradient, what can I tell? Okay. So suppose I draw a straight line, and I tell you the slope is -2. Okay. So this straight line is having a slope of -2. And suppose I am at a current point, okay, which is point, and this point is what? Let us say I am at the point 0, and the function value is, so this point is 0, this point is 7, okay, and I take a small step towards the right. I move epsilon bit here, okay. So at the new point, what is the function value? Who can tell me now? So what is this function value?
Less than 7.
How much less than 7? You look at the slope. Slope is -2, and this difference is epsilon. So how much would this be?
5.
You are close, not 5. 7 minus 2 epsilon. Very good. Okay, because the slope is -2, and I am moving epsilon bit here. So the difference would be 2 epsilon, -2 epsilon. So the new function value would be 7 minus 2 epsilon, right? Everybody agrees? Okay.
Yes, sir.
So this -2, this is exactly your gradient, right? Your function was like this. Your nonlinear function was like this. And at this point, you computed the slope by looking at the derivative. So that derivative gave you the slope. Okay. And what this derivative tells you is the approximate change in the function as you move slightly. Okay. So the nonlinear curve will have a different value. It will not be 7 minus 2 epsilon. Take a linear approximation to it. Okay. So I have a nonlinear function, and I am at a current point. Okay, as you can see in the picture, I'll make a green dot. Okay. So this is my current point x naught. Okay. At x naught, I evaluate the function value as fx naught. Okay. I don't know how much my function will change if I move along this curve. Okay, because it is some complicated nonlinear term. Instead, what I do is I create a linear approximation to it. Okay, and I look at its slope. Okay, and I say that in the neighborhood of this point, right, if I draw a blue box around it, okay, this green line is a good approximation of the white line. Okay, so I can say that the function value of the white line will be approximately same as that of the green line, and I know what is the value of the green line. It is just f of x naught plus whatever epsilon I am moving times the gradient of f of x naught. Okay, this is my slope. This is how far I am moving. Okay, so this is my step length. Okay, this is the function value at point. Okay, so the function value at the new point. Okay, so what is the function value at the new point is the function value of the old point plus epsilon times gradient of f of x naught. Okay, nearly. Okay, so the beauty of this approximation is that I don't have to evaluate fx1. Okay, so without even computing function, suppose my nonlinear function was very complicated, right? I don't need to evaluate it. I just look at the old value and I know how much I have moved slightly, and I have evaluated the derivative at the old point. So just by looking at these three, I can make a good guess of what is the function value at the new point. All right. If you want a even better approximation, right, than this, what can you do? Who can tell me? So to get an approximation, I use the first order derivative, which is the gradient of f. Okay. Now, if I want an even better approximation, what can I do? Can I use an even better approximation than this first order approximation? Who can tell me? If first order approximation is good, then second order approximation is even better, isn't it? Okay. So if this gradient sign is too confusing, let me just write it as f prime. Okay, which is the derivative of f. Okay. Who can tell me what is the second order approximation? Second order approximation is this: half times epsilon square f double prime of x naught. Okay. And what does this series remind you? Who can tell me what is this series?
Sir, Taylor series expansion?
Yeah, exactly. So whatever you read in your Taylor series in Math 101 or first course in mathematics in your BTech or BSc or any undergraduate program, that is the central piece in optimization. Okay, so what you do, right? So in your optimization, you don't know what is the shape of f because it is a complicated nonlinear function, right? So you change this, okay, to some other point which is already known. So you know the function value at the current point, and you say this is your step length, this is your epsilon, and this is your derivative. Okay, so this is your first order approximation. Okay, so there is a small thing here. So there's a decay here. So the direction in which you move. Okay. So in one dimensional case, okay. So suppose I'm in a one variable case. How many directions are there in which I can move? So again, let me. Very much, very much, very much. These errors will accumulate. Every now and then you will have to do something to fix those errors. Okay, I'll come back to that. Okay, so again, imagine a one-dimensional case, and now your vertical axis is the function value. Okay, so now you are at some point. Let us say 0, 0, or just 0. Okay. So now suppose you are at x1 and you want to move somewhere. Okay, how many directions are there in which you can move? Who can answer that? Quickly, we are running out of time. There are only two directions in one-dimensional case. Either you increase x1 or you decrease x1, right? There is no third direction, right? So that's why there is no decay term in one-dimensional case. But when x is multi-dimensional, your gradient has to be multiplied by the direction. Okay, so this approximation x naught plus alpha k times d times gradient of f. Okay, so in steepest descent, this direction is chosen. Okay, so this dk is chosen to be minus of gradient of f. Okay, at xk. Okay, so in that case, what is the new function value? So it is f of x naught minus of alpha k gradient of f of xk transpose the gradient of f of xk. Okay, so this term is always positive, right? If you take a vector and multiply it with itself, this will always be greater than equal to 0. Okay, so that means that if you choose this direction to be negative of gradient, there is a guarantee that the function value will go down. Okay, so that means this this new fx is always less than f of x naught. Okay, in a neighborhood, in a small neighborhood of x naught. Okay, because this first order approximation is valid only in a small box around it. Okay, you can't go too, this white and green become too far away. Okay, so is this understandable, that I choose a direction which is the negative of the gradient, which gives me a guarantee that if I choose this direction in a small neighborhood, my function value is bound to go down. There is no way it can go up. Okay, so this steepest descent is a very important unconstrained optimization algorithm. Okay, it converges. So there is a theorem. Okay, so the result, the well-known result is steepest descent converges to a local minimum, to a local point of stationarity, or local minimum, or a stationary point, no matter where you start from. So it doesn't matter whether you start from 0, 0 or 100, 100 or anywhere else. Point number 2. Okay, it's a great algorithm. Okay, not many algorithms will guarantee you that it will always converge. Okay, steepest descent gives you a guarantee. Okay, so in that way it is very good. Okay, but nothing comes for free, especially in nonlinear optimization, and it is well known that steepest descent is slow. Than many other methods. Okay, but the good part is that steepest descent has a guarantee of convergence. Okay, so if you do steepest descent and you are patient enough, then it will definitely lead you to a stationary point or a local minimum. Okay, and here is an example of why it can be slow. Okay, so I'm going to go too fast now. Okay, so stop me if you don't uh, understand something. Okay, so I'm going to draw some ovals. So this is a contour plot of some quadratic function. Okay, so if you do steepest descent, okay, sometimes it may happen that your algorithm actually zigzags. Okay, so so let's start from a point here. Okay, so if I draw a tangent to this curve, if I look at the gradient direction, it will be the perpendicular to the tangent. So you will go somewhere like this. Okay, and the next step would be perpendicular to it. I'm sorry, I'm weak in drawing geometrically. Okay, and then the next step would be the previous direction. With a little bit of analysis, you can actually show these things. Okay, and the next step would be perpendicular to the old step. And then the next step would be perpendicular to the old step, and so on and so forth. Okay, so if I draw the path, you know how so the center point is the actual minimum, but if you trace the trajectory that steepest descent method will take, okay, it will go something like this. It will look like a series of steps, okay, perpendicular directions, which become slower and slower, you know, smaller and smaller in step length. And only in the limit, you know, after many iterations, it will converge. Okay, so it will take many iterations. Okay, all right, and this is seen even with simple functions like quadratic functions. Okay, so for example, suppose I tell that here is a problem, right? Let's say minimize 20 x1 square plus x2. Okay, and my starting point is let's say 1 1, not 1 1, let's say -5 -5, you know, something like that, right? So then it will take many iterations to actually reach the optimum point, which is 0 0, which we know already is the optimum. This method can be slow, but it is guaranteed to converge. Okay, it will not. It can be slow, but it's like fixed deposit. Okay, you will not get very high returns, but you will get returns. Okay. Okay. There are other methods which will take you from this point to the optimal point very fast, and those are called Quasi-Newton methods. So they are almost like steepest descent, but the direction choice of direction is not this negative of the gradient. It is close to it. It is minus of hk times gradient of f of xk. Okay, so what you do is you choose the steepest descent direction, which is the negative of the gradient. Okay, and multiply it with some positive definite matrix. Okay, and this hk is updated in every iteration. Okay, and how you update is it depends on the method. Okay, so there are two well-known methods in this category. One is called the Bfgs method. Maybe some of you might have heard about it. It is named after the four people who invented this method. It is Broyden, Fletcher, Goldfarb, and Chanot. Okay, so names of four mathematicians who devised this method. And also there's one more method called DFP. Both different ways of updating HK. Okay, and these are much faster than steepest descent. Okay, so for the same problem, okay, quadratic contours that we saw, if I draw the yellow curve for these methods BFGS and DFP, what they do is they incorporate second order information also, right? So the why are they faster is they use some second order information also. Okay, so they don't just look at the gradient, they look at how the gradient changed in the previous iterations and try to use that to converge faster. Okay, so for this particular thing, they will not go in the direction of the steepest descent. They will change the direction slightly, because when you multiply some direction with some positive definite matrix, it tilts it. So it will take this yellow direction. It will not but go closer to it. Okay, something like that. And in the second iteration, it is guaranteed to reach the center. Okay. So in two iterations, these quasi will converge. Okay, so if I draw this separately on the same thing, so it will take a step like this and then go directly to the. Okay, so in two iterations for quadratic functions in two variables, it is guaranteed to reach the optimal point. Okay, which is fantastic, as compared to steepest descent, which might take about 50 steps. Okay, this might take only 2 steps or so. Okay, so these fast, these BFGS and DFP, they are fantastic, blazing fast methods. Okay, so two results that we should care about. Okay, there are examples. Okay, sometimes fail. Okay, sometimes don't converge, but that is rare. Okay, you have to create some functions where these won't converge. For most functions, they will usually converge. Okay, and they are blazing fast. That's something I wrote earlier also, said earlier also, blazing fast as compared to steepest descent. Okay, and the third property that is what multiply a matrix HK times some vector. Okay, so this might sometimes be expensive operation. Okay, so sometimes not possible, sometimes difficult. Okay, why would this be difficult? Because suppose I have 1000 variables, okay, which is not uncommon. It is quite common to have problems with 1,000 or even 10,000 variables. So suppose I have a 1000 variable problem. So that means the size of HK would be 1000 cross 1000. Okay, so that is a big matrix. That means you have to store 1 million entries because it is a square matrix of size n cross n. Okay, and in some machine learning problems, the number of variables is in fact 1 million. Okay, so if you have 1 million cross 1 million matrix, that is already 10 to the power values. Even if it is very sparse, it is very difficult to store. Okay, so then you are talking about 1 trillion entries. Even if it is very sparse, you would still have, you know, about 1 million entries or so, which is hard to store and then compute this product. Okay, so you need some other methods like conjugate gradients or some, you know, some other momentum type of ideas. So which we will not go there. But you know, this line, you know, how you find directions and how much you move, even for unconstrained problems, is fairly interesting, and a lot of work is happening even now. Okay, any questions on this? Because we have 3 minutes to cover the whole of constraint optimization also, which I want to do. So so any questions?
No,
Can
sir.
directly answer this question about errors in accumulation. So so what you do is, after every iteration, you evaluate the function at the new point and evaluate the gradient also at the new point. So some of these errors taper off and don't accumulate, but some other numerical errors may accumulate because on computers, anyway, even if you do everything exactly, when you do computations with floating point numbers on a computer, there will be some errors. Okay, so so computers don't store rational numbers; they only store decimal numbers by default. And so, for example, if you store 1/3, it will store it as 0.3333 up to 16 digits, and later on it will truncate. So that is already an approximation, right? So those things can actually blow up. Okay, but other than that, the errors because of approximation to linear curves, they don't usually add up, because after every iteration you reevaluate the gradient at the new point and the function value at the new point. Okay, so with that, I'm going to stop my discussion on unconstrained optimization. Okay, I will come to constrained optimization, because in Scilab we will do some examples of constrained optimization also. So in about 3 minutes, I'll try to just give you a summary of what these constrained optimization ideas are. Okay, so very quickly, in a geometric view, so suppose I have this problem. Let's say minimize x1, and suppose there are 2 variables. Okay, so I'm in 2 dimensions. So there are 2 variables, x1 and x2, and I want to find the minimum value of x1, but with some constraint. So I say that let's say x1 square plus x2 square is greater than equal to let's say 4, and same constraint, let's say 4x1 square plus x2 square is less than equal to 16. Okay, so geometrically what are we doing? Okay, so let me draw the feasible region. Okay, so if I look at the set of all points which satisfy this constraint, okay, so what would it look like? So 4x1 square plus x2 square equal to 4 is an ellipse. Okay, so if I draw the curve 4x1 square plus x2 square equal to 4, I will get this ellipse. Okay, so I am in 2 dimensions. Okay, so if I say 4x1 square plus x2 square is greater than equal to 4, that means I must be outside this ellipse. Okay, so that means I'm not allowed to come inside this ellipse. I want to stay outside. Okay, and the next constraint, okay, what is the next constraint saying is that 4x1 square plus x2 square should be less than equal, right? So that is a bigger ellipse, and that is saying that everything should be inside it. Okay, so the feasible region for this, the points which satisfy all constraints is this ring. Okay, in which the first constraint is the one inside, the second constraint is the one outside. Okay, any doubts on this?
No, sir.
Okay, so for example, if I look at this point, let's say 1, 1, is it feasible? It is feasible, right? Because it satisfies both constraints. At 1, 1, 4x1 square plus x2 square is 5, so which is more than 4 and less than 16. So this point is allowed. Okay, but 0, 0 is not. Okay, because it lies outside the first constraint. Okay, so within this region, what is the minimum value that x1 can take? Okay, so remember that x1 is increasing towards the right, decreasing towards the left. So the minimum point is this one. Okay, minus 2, 0. Okay, I can't go any left of it. Okay, if I want to find, then I need to go towards the left of this point, minus 2, 0. Okay, but this constraint is stopping me from going towards the left. Okay, so at this optimal point, what should happen is that the gradient of the constraints should be some combination, the gradient of the objective should be some combination of the gradient of constraints. Okay, so you can write, so how are these problems solved? Okay, to solve these problems, again you rely on first and second order approximations. Okay, so the solution methods you look at first and second order approximations of f, okay, your objective function and constraints. Okay, and then you write a simpler model. So you write a first order approximation. So first order approximation of my objective function in this case would be x1, because it is already linear, so I don't need to approximate it anymore. Okay, next I will write a first order approximation of this constraint, then a first order approximation of this constraint, and then what will I get? I will get a linear program. Okay, I will get a linear program and I can solve it using simplex method. Okay, that many of you might be familiar with. And then move to the new point, and then again compute a new first order approximations, then again solve using linear programming and get a new point. Okay, so this is called successive linear approximation. Okay, So the algorithm I just described, you take linear approximations, then solve linear program, then again new approximations, again solve. That is called sequential linear programming. Like steepest descent, this is okay, but it will be slow because we are ignoring second order information. Okay, when you also take a second order approximation, then you get quadratic approximations, and you get something called quadratic programming. Okay, in sequential quadratic programming, you take second order approximations of the constraints and the objective and move all the quadratic terms into the objective. Okay, so it's a very nice trick, and it works really well. Okay, and it is much faster than your sequential linear program. Okay, and then there is a different set of methods called the barrier methods or interior point methods, which so maybe some other time. Okay, so it's already 11 o'clock, and time to move on to do some numerical examples ourselves. So what I suggest is that we can take a short break, about 5 minutes. So it's 11:06 in my watch. At 11:11 we can start again, and we will start doing things in Scilab. Okay, so if you have some really quick question right now, you can ask. If you don't have any questions, you can start having water or take a break or whatever. If you have questions, you can hang around. I'm ready to listen to any questions. But these are very interesting topics, and some of the books that I mentioned